I'd like to begin by telling you what an honor it is to be here this morning. I find myself more and more in meetings with fellow bureaucrats where we talk about the people who actually do the work. And I look out here and I see a lot of people who are really doing work. And it's easy to just go about your day and think that's just sort of normal. It's not. You represent what I think is a national treasure of knowledge and experience. There are so few people. You're such a low-density, high-demand asset for our nation that it's just really a privilege to be here. I want to talk to you today about some of the things we think we can do with research development, testing, and evaluation. And so we're going to go through each one of these and talk a little bit about how we prioritize research needs, how we might go about cataloging future plans, what would be involved in a gap analysis, and how much would all this cost, and what kind of facilities might you need. Identifying and prioritizing the needs, we got a lot of help in the NAS report on how to do that. And in fact, if you pull that up in Adobe Acrobat and search for the word research, it appears about 430 times in that report. There's a couple of recommendations here that specifically deal with research. Recommendation 3, establish validity of forensic science methods. Recommendation 5 talks about human observer bias and sources of human error. And then recommendation 12 was very specific. It was about fingerprint interoperability, but it gets at a larger issue to me, which is this idea of just doing things better, faster, and cheaper in forensic science. So we'll talk about that. And then recommendation 10, we overlap with the education working group a little bit of this research has got to be done with our centers of excellence and academic partners. And so let's talk a little bit about a few of these research needs here. I view the research needs really, you can put it on a timeline, right? There are past needs, present needs, and future needs. The past needs are things the NAS report said, geez, you guys should have already done this. Before you say no two fingerprints are the same, you know, can you get me a citation in Nature or Science that shows that no two fingerprints are the same? Those kind of things, the foundation of our science. And so, you know, there are a host of things where we do comparisons and make conclusions where our intuition tells us we're on pretty firm ground, but we probably need to back that up with some foundation. In my mind, I'd love to see some studies like this. You know, so you give some fingerprint examiners a fingerprint and 2 possible timprint cards and say, does it match? Can you tell me if it matches? I think most qualified fingerprint examiners would have no problem with that, but then you could say, can you tell me now? How about now? Can you tell me now? And sooner or later, we'll find a limitation. Now, what should appeal to most of you as scientists out there is the amount of fingerprint that we give them, we can actually measure, right? We can put that in terms of an area, and we can keep track of that, and we can put that on a graph with an X and a Y axis, those kinds of things. I think, though, if we're honest with ourselves, all of our disciplines have had a culture that's a little bit against this. And although I can't attribute this quotation to any one person, I think we've all heard it, which says, no, don't do a study like that, because I don't want some defense attorney telling me that I didn't have enough of a fingerprint. I want to have the flexibility to make a call on that fingerprint if the case is important enough. And so probably from an ethical point of view, we need to take a step back and say, you know what, we really do need to do these studies. We really do need to know when we stop being able to predict fingerprints, when there's no other case information telling us that we really wish we could. Peer-reviewed research on uncertainty, accuracy, and reliability, those would be on my timeline the things that we probably need to do now. And I put that slide up there to remind me that we don't actually have to invent the wheel on this one. And if we do, it might look a little bit like that. The larger scientific community and medical community have been dealing with this issue for a long time. And in fact, if you grab an analytical chemistry textbook, sophomore level textbook, these things are well described. We teach them to undergraduates all the time. The first thing is this notion right here that anytime we measure something, it's going to probably give us some sort of bell-shaped curve. We don't get a perfect measurement. And even the measurement we take, whether it's how long something is with some measuring device, I'm going to have to make an estimate of, is that 25.5 or 25.6? At some point, I'm making a guess. And so we're going to get bell-shaped curves. The next thing would be that often we're asked to compare things. And so those 4 different samples there all have the same average value. right? But they're different types of samples. So many of you have dealt with this. It'd be something like a student's t-test of how successful are we at really differentiating those things. Those kind of things are well described. We don't have to invent it. Now, the final thing is that all deals with uncertainty of measurement. The final thing is we render conclusions and opinions, very well-informed expert opinions, mind you. I'm not throwing a rock at that. But we have to make a decision, and that decision might be, if you're above the green line, we're going to say you're intoxicated. If you're below it, we're going to say that you're not. Or if you're above the green line, we're going to say you're pregnant. And if you're below it, we're going to say you're not. And where we draw that line, there or there, means we get some more false positives or false negatives, right? And so that's pretty well understood. If you get a medical diagnostics textbook, you'll see something that looks like that. That's called the receiver-operator characteristic curve. It was actually developed shortly after Pearl Harbor in World War II to help us keep track of how we would look at radio signals from airplanes and decide if they're friendly or foe. All right? But it really is about comparing true positive rates to false positive rates. If you're unfamiliar with that diagram, I learned about it probably in the last couple of years, so I assume everyone's got my same level of ignorance. That line, the diagonal line, is what a coin would get you. Flipping a coin would put you on that diagonal line. So as it diverges up and to the left, it means you've got a test that helps you differentiate things. All right, this one's fascinating to me, this idea of extra-domain information. This is something that plagues all branches of science, but I think if we're honest with ourselves, we're particularly susceptible in forensic science. And it goes like this. The swashbuckling, handsome detective, could be Ken Melson, comes in to the horn rim, sort of geeky scientist, and says, I need you to compare some evidence. I need you to do something for me. But before you do it, I got to tell you a few things about this case. This guy, we think he's killed 2 people, and we got this fingerprint right where it should be. It's on the gun, and we want to compare it to him. The other thing I want you to know is we had him last year dead to rights, but he got some fancy attorney, and he got off on a technicality. So I'm going to give you the evidence here, and if you can just tell me what's underneath it, I don't want to influence you at all. Right? I mean, we have all seen that play out in some shape or form, whether it's in our own disciplines, in the medical discipline. Doc, before you look at this CT scan and tell me when this injury occurred, I want to tell you a little bit about the case. It occurs. You know, the problem is we're just not real good at that, right, as human beings. We start seeing what we want to see. So science is the drive of science is how do we just get that out of the equation? So really we just get handed that and someone says, start there. That's all you need to know. Maybe I'll give you something to compare it to. The other one is this notion of sources of human error just beyond bias, right? I come from the DoD setting, and one of the laboratories that may help us with this, they got real excited when I began to have this dialogue with them, was the Air Force Research Human Factors Lab, right? Because they'll look at an F-16 and say, that's an F-16, but when you put a pilot in there, she becomes part of the F-16. It's not just a person anymore, it's the limitations of that person. And so, you know, you can Google and find these. The one that really hurts my head is that line is just as long as that line, right? There's some limitations we have. And there's an interesting dynamic that goes on here. If I were to hold up a digital camera and say, let's talk about the limitations of the CCD inside there, we'd all go, okay, no problem. If on the other hand, I point to your eyeball and say, let's talk about the limitations, we get personally offended. It's my eye. It's my eye we're talking. It's not even limitations. It's a great-looking eye, right? We get offended when it's about our own limitations. So science helps us sort some of those things out. So recommendation 12 I talked about was fingerprint interoperability. In my mind, that translates to a much larger research and development need, and that's better, faster, cheaper. My first experience as a lab director, my deputy came in who kept me from getting fired for the better part of 2 years and said, boss, as you learn more about this job, you're going to say that you want to do it better and faster and cheaper, and I'm just going to teach you this on your first day. You can only have 2 of those. Pick any 2 you want, but you cannot have all 3, right? I mean, we can get it better and faster, but it's going to cost, right? And we can certainly do faster and cheaper, but you're not going to like it, right? So but research says in the future, yes, we can. We can give you better, faster, and cheaper. And you know, it says, how do we take something like that and turn it into something like that So the people who look like that can transition to people who look like that, and we give them that capability. And so, you know, and we've all seen this, right? If we grew up watching Star Trek, we're talking about the tricorder, right? Spock order, right? You walk in and there's 4 human life forms. This one matches that one. This one has that much alcohol in the system. So that's where research really would be taking us. How do we do it better and faster and cheaper? All right, so some of the challenge we've got to face is, how do we find out what's going on out there already? In my limited world, just within the Department of Defense, that's what I've been sort of tasked with. And you can do that from a top-down point of view, send out formal requests, and you get some good responses. But you get things that have been sort of formally approved programs of record. The real challenge is initial concept ideas come from folks like you who are working in the field every day and comparing things and looking at things and realizing the limitations of things. And that seems to happen from the bottom up over a cup of coffee right out here, right? And so how do we do that? Gap analysis is pretty straightforward, right? We're going to take those priorities and then figure out what's going on, and then look for overlaps. Are there things that several agencies are doing that we could maybe change the focus so they harmonize better? Or could we even transition and say, look, 7 of us are doing this very similar DNA project, but no one is doing this work on this paint comparison. Maybe we need to shift some of our efforts around. And then we would hopefully discover the really true gaps. What are things that need research that nobody's looking at all? Identifying the cost associated with RDT&E. I was just having this talk with Robin before we got started this morning. This is tricky, right? Because if we knew the answer, it wouldn't be research. You know, so if someone says, well, how much is this going to cost? I have no idea. Well, could you take $1 million? Sure. Could you take $1 billion? Absolutely. You know, if we gave you $200 million on this project, what are we going to get? I have no idea. I hope something good. I hope, but we don't know. That's the nature of research. So we design good experiments and hope that we can begin to investigate things and they'll inform what we're doing. The biggest cost, though, I think, is this opportunity cost on the top. So how many people are involved in forensic examinations in the room? Sort of show of hands. Yeah, lots of you. And how many of you have some sort of backlog? If you had your hand up. Okay, so how many of you, if you have both hands up now, I can say you're probably in the group that doesn't have free time, right? But you're the people who are the smartest. You're the people who know the most about this, who know what those research needs are. So finding ways to not grind to a halt casework so that we can begin research is going to be a challenge. There are lots of places out there, and so this will be part of it. How do we partner with these places? How do we identify them? How do we offer incentives for them to work with us? All right, so just summing up, those are the few things we talked about. That bumper sticker on the bottom is really the most important, though, because this has got to be such a team effort. There's just more rice than we can eat, more rice than we can each keep in our own bowl. And so I look forward to talking with all of you and the way ahead on the future here. That just gives you a little indication of the type of people we already have on the research and development team and the breadth of experience. And thank you very much.